Now we want to take some time to think about how we actually calculate values of heat. So we're going to start with units. Heat is an energy unit. It's always going to be described in energy. And so our standard metric unit for energy is the joule. And so when we're talking about heat, we always use joule. This is a person's name, so why it's spelled like that. The symbol is a capital J, but technically when we write the unit, use a lowercase j. Joule is not a ton of heat, so or a ton of energy, so it's really common to see kilojoules, much the same way that we use kilograms for like pounds of people. A lot of energy amounts are in joules. You may be familiar with a calorie. A calorie is kind of the standard customary unit for energy. It has to do with, it's the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So 1 calorie is bigger than a joule. It's 4.184. So that is a customary to metric conversion. The one is exact, 4.184 is approximated. This is more common in a biological context. We don't use it as much in chemistry. You will note, you're probably familiar with it from a food label. So calories on the food label, you'll note there's a capital C there. What that actually means, that capital C is actually a reference to kilocalories. So 1 calorie, 1 capital C calorie on like a food label is actually enough energy to raise the temperature of a kilogram of water by 1 degree Celsius. So 2,000 calories is enough energy to raise the temperature of 2 million grams of water by 1 degree Celsius. So your body uses a lot of energy in a day. You may be familiar with other temperature units. Kilowatt hour is most common in electrical usage. British thermal units, as the name implies, is most commonly used in heating. So those units just have relationships to calorie and to joule. They're defined conversion factors. They're a lot bigger. You'll note 1 calorie is not a lot of kilowatt hours and not a lot of British thermal units. Those are more kind of practical units that, again, describe kind of the size, the magnitude of heat that we tend to use, and the amount of electricity that people tend to use. Your house uses a lot of energy as electricity. So when we're talking about kind of moving heat and quantifying how heat amounts, we know that the amount of energy required to raise the temperature of an object is going to depend on what we're looking at. And so heat capacity, which is a capital C, is the ratio of temperature change to heat added. So just because you put energy in doesn't mean the temperature will always go up by the same amount for different objects. It's going to depend on what you're heating and how much there is. So we know kind of qualitatively it makes sense that if you have, say, a little pot, it's easier to heat that up, whereas if you have a big pan, it's going to be relatively more difficult to heat that up, just because there's more of the pan to heat up. So we know with heat capacity, these are both cast iron, so if you have the same pan, the bigger one is going to require more energy. The other issue would be what you're looking at measuring, or what you're looking at heating up. So one of the reasons why we use metal pans or metal pots to heat things is because it's relatively easy to heat up a piece of metal. So this pot will get very hot pretty quickly. It's going to take a lot more energy to raise the temperature of water. So different substances have different tendencies, or the different abilities to translate that kind of energy going in to actual temperature change. Because remember, actual temperature corresponds to average motion. So just because you're putting the energy in doesn't mean you're making the molecules actually move faster. For some molecules, it requires a lot of energy to really get them to move. To account for this, we use what's called specific heat, or specific heat capacity. This is a lowercase c. It is much more common that we use the lowercase c. You will see sometimes people drop an s to specify that it is specific, or S on a capital C. I'm going to use a lowercase c. That is the most common that we see. And so specific heat is not just the energy needed to raise the temperature, but the energy needed to raise the temperature of 1 gram of the substance. So the idea of specific means per 1 gram. That's what that word means in this context. And the idea of specific heat is that you account for, that kind of, if you want to heat something up, do you have a lot of it and what are you dealing with? Specific heat allows us to only quantify the question of what are you dealing with. So specific heat is intensive, okay? So it is a property of each substance. So water as a liquid has a specific heat. Air with a certain humidity has a specific heat. Aluminum, silver, plastic, any of these materials have specific heats. So you can actually use specific heat to identify a substance, just like we did with density, or we saw with density, molar mass, those sorts of ideas. Similar to those, you can also look them up. There are tables of specific heat capacities that you can find for all sorts of things. You'll note that the units, also similar to those other intensive properties, are just these compound units, joules per gram degree Celsius. So gram and degree Celsius are going to be in the denominator, joule is up top. And you'll note if you look at these, they kind of go over ranges of magnitude, but you'll note water, independent of its phase, is really high. The specific heat capacity of water is really, really high, especially relative to a lot of other objects or a lot of other materials. And so as a result, what that means is really high heat capacities mean you need a lot of energy to increase the temperature of the water at all. And so this is why we use water to cool things, because this kind of capacity, what this language comes from, is you can put a lot of heat into water without really seeing the temperature increase very much. So that's why we use water to cool things off, because other things you can need not a lot of energy, say pieces of metal, we can see they're all really low heat capacities. Not a lot of energy really can get the temperature to change quite a bit. So you can really cool it down by pulling out not a lot of energy. This also corresponds to why it feels so gross in the summer here. Water as a gas has a really high heat capacity still. And so when you go outside and it's really humid, it takes a lot of energy out of your body to change the temperature of the air around you, right? The air around you is hotter than your skin, so it's putting energy into your skin, and there is a lot of energy for that temperature of the air to cool down. And so that's why it feels hot in the summer when it's humid, because the air is there's a lot more energy in the air for its temperature because there's a lot of water in the air. When it's dry, all that water's gone, and air is a really low heat capacity, except for the water in it. So when we actually want to calculate heat for temperature change, our equation is going to be Q is equal to mc delta T. So Q, lowercase q, is still going to be our heat. M is mass of the object that's temperature is changing. C is the specific heat capacity. And again, that's just a property of the object. So if you know something's temperature is changing, you just take a look at what the object is. You can look up that specific heat capacity. Delta T is then the change in temperature. So this delta that we see right here, that's a capital D in Greek. So it stands for difference. And so delta always means change. So we're going to see a decent number of deltas. That always means the final value minus the initial value. So one of the things we can start to see from this is that heat always characterizes a change. Heat is not a static process or a static object. Things just don't have heat. They have energy inside of them. And heat is the process by which that energy changes corresponding to temperature changes. When you see a thermal flow or transfer of energy. So heat is always associated with a change. Heat is the change. So how much heat is required to raise the temperature of 10 grams of copper from 25 degrees Celsius to 40 degrees Celsius? What do we want? Heat. Okay, so for now, we only have one equation for heat. We're going to see some other equations and kind of processes. Overall, we're going to get three relationships that describe heat. But our first one that we have here is based around temperature change. So whenever you see, temperature changes going on, especially you want heat to raise the temperature of something, that's where Q is equal to mc delta T. You're looking at kind of the static change. The object is static. This piece of copper isn't changing in any other way. There's no chemical process, no phase change, no anything like that. You're just changing its temperature. So it's just a question of, do we have the necessary variables? Those variables are mass, specific heat capacity, and delta T. So we want to know how much heat is required. And we're looking at raising the temperature of this piece of copper. And so for now, we're going to be dealing with a lot of versions of heat. And so one of the things that's unique about this chapter is we're going to be dealing a lot with equations now. So there's going to be a fair amount of equations to work with. And so there's going to be a couple of equations and processes for calculating heat. We want to think about which one we're working with here. And the thing we want to key in on is the fact that the temperature is changing. This is the heat associated with a temperature change. So our equation there is going to be Q is equal to MC delta T, where Q is our heat, M is our mass, C is our specific heat capacity, and delta T is the temperature. And we said that Q, heat, is what we wanted to know. And so, because it's an equation, the question is, well, what about everything else? Mass, specific heat capacity, and delta T. Well, mass, we're told, if we're looking at the heat temperature of copper, the mass is 10 grams. Okay. We're also given temperature change, or the temperature values. You'll note delta T would be the temperature change. Here we can see we're given the endpoints. So delta T is going to be TF for final minus TI for initial. Okay. And so one of the things we can see is that it's from 25 to 40. So we know that the final is 40 degrees C minus 25 degrees C. So then the question is, what is the specific heat capacity? Well, specific heat capacity is an intensive property that's associated with a substance. And so in this case, because we're dealing with copper, once we learn the name, that tells us what the specific heat is, and we can look that up. There's tables, that's a piece of reference information. You can't necessarily find it on the periodic table, but it's similar to looking up molar masses. It's just something we can always look up. 385 joules per gram degrees Celsius. All right, so we got all of our variables figured out. Let's go ahead and plug them in. Q is equal to 10 grams times 0.385 joules per gram degrees Celsius. And then 40 minus 25 is going to be 15 degrees Celsius. So I can see for my units that the gram cancels out this gram in the denominator, degree C in the denominator, degree C in the denominator. So all that we'd be left with for our units are joules. And then 10 times the 0.385 times the 15. 58. So joule is a heat or an energy unit, which is good. Heat should always have units of energy. And so again, we're going to be looking at calculating heat. So far, this is the only equation we have. The only method. We'll learn two other methods that we can figure out heat. And so we can see is that temperature change right there. This is always the equation that we want to use to work through associated with temperature changes. And that's kind of the indication. If something's heating up or cooling down, specific heat is going to be our tool to figure it out. We can take the same prompt we had for heating up copper, and we can change it, and the only thing that we replace is 10 grams of water. Okay, so the only thing we've changed is the substance. And so the only thing that will affect is what the specific heat capacity is. Water's specific heat capacity is 4.184 joules per gram degree Celsius, which is quite a bit higher than the 0.385 that we had for copper. So water has a higher heat capacity. As a result, more energy is required to see that same 15-degree temperature change, right? To go from 25 to 50 requires 10 times as much energy. And so temperature, if you remember, is that sort of average thermal energy, how much motion those molecules have. So at 40 degrees Celsius, it doesn't matter if it's water molecules or copper atoms, you're describing the same relative amount of motion. But water molecules are just more difficult to get to move around. So a lot of energy is required to see that same temperature change. Again, this is why we use water is really special in having this really high heat capacity. That's why we use water to cool things off, because you can say put a ton of energy into the water and you won't really get unsafely hot water. And you can really cool things down. That final temperature at the end is going to be not that hot, right? When all the heat flows between hot and cold objects, you get down to say whatever they're all at the same temperature, it's going to be relatively low because you're using water. And you can use lots of water, so that bumps you up, right? You can make this number real big, and then you're going to really get real small temperature changes. Water's real cheap, water's really abundant, and it has a really high heat capacity, and that works really well. Has a lot of useful applications.